Welcome grade 12s to STEM in Action's Boost series. I'm V Guyan and today we're going to have a look at chemical equilibrium part 2. Just to remind you of some of the pre-knowledge that you should know from grade 10 and 11, the kinetic molecular theory and phase changes, which include the solid, liquid and gas phases. We also should know the chemical formulae and naming and our balancing of chemical equations. And of course enthalpy and endo and exothermic reactions and the work that was covered in chemical equilibrium part 1. In this segment we'll be having a closer look at Le Chatelier's principle. Le Chatelier's principle says that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So what does this mean? If we have a look at changing concentration in an equilibrium, that equilibrium is going to shift, say, to the right if we added more products, and so that it can re-establish the equilibrium. And you can see this displayed in the GIF on your screen at the moment. So concentration, what happens is if we increase the concentration, it's going to favor the reaction that uses up that extra substance. So if you increase the concentration of the reactants, it will favor the forward reaction. If you increase the concentration of the products, it will favor the reverse reaction to use up the extra products. If you decrease concentration, it will favor the reaction that will produce more of the substance that you have decreased. So then we get on to temperature. Temperature is another factor that can disturb the equilibrium. And so Le Chatelier's principle tells us that if we decrease the temperature, the reaction that produces more heat will be favored. This is known as our exothermic reaction. If we increase the temperature, the reaction that uses up that extra heat will be favored. In other words, our endothermic reaction. Remember that temperature change will affect both the forward and reverse reactions. So if we increase the temperature, the rate of both the forward and the reverse reaction will be increased. But however, one reaction will be favored more than the other. The third factor that can affect equilibrium is pressure. If we increase the pressure, it will favor the reaction that will decrease the pressure on the system. This is the reaction that produces the least number of moles of gas. On the other hand, if we decrease the pressure, the reaction that increases the pressure on the system would be favored. That's the reaction that produces more moles of gas. We can see this by having a look at the GIF that is on your screen at the moment. If we decrease the volume, we can see that the pressure then will increase, and that favors the forward reaction, which produces less moles of gas. And we can see this by more AB being produced. As we increase the volume, we are therefore decreasing the pressure, and so the reverse reaction will be favored that produces more moles of gas, produces A and B. So to summarize, the three factors that will affect our equilibrium and cause it to shift are concentration of aqueous solutions, the temperature of a system, and the pressure when we're looking at gases. This becomes particularly important when we look at industry, where the yield of reactions needs to be accurately predicted and of course maximized. Right, so then the last thing we need to touch on when we're talking about factors is the factors that affect the value that we'll get for Kc. There's only one factor that will affect the value we get for Kc, and that is temperature. And this is why in the exam questions you will see they state the Kc at, and they'll give you the certain temperature that that Kc is at, because if the temperature changes, the Kc value will change. So for any reversible reaction, Kc is specific to a specific temperature for that reaction. If there's a new temperature, we need to recalculate, find our new Kc value. Often a catalyst is thought to be a factor in equilibrium where it is not. A catalyst does help the reaction reach equilibrium faster, but a catalyst increases the rate of both the forward and the reverse reactions, and therefore it does not change the equilibrium. So how will this most often be seen in exams. Most often we'll have a look at our graphs. And we have two main types of graphs. The first one is the rate of the reaction versus time. And there we can see an example of this type of graph where we've got our forward reaction that obviously starts with a high rate because you've got a lot of your reactants. And as your forward reaction takes place and you are forming products, the rate of your reverse reaction then starts to increase. Once we have products, the more products we have, the more our reverse reaction can take place, until it gets to such a point as the rate of the forward reaction and the rate of the reverse reaction are equal, and we can see that as the straight line going across the graph there. So how will the different changes in the equilibrium affect the rate of the reaction graphs? The first change, a change in concentration or pressure, and I've grouped these two together because they'll look the same on the rate of reaction graphs. We'll get a sharp increase in the rate of one reaction and a sharp decrease in the rate of the other reaction. The second effect is the change in temperature. The change in temperature, remember, will affect the rate of both reactions, but one will be affected more than the other. And thirdly, if we have the addition of a catalyst, we will increase both the forward and reverse reaction rate by the same exact amount, but they will stay at equilibrium. So the second type of graph we can get is the graph of concentration versus time. And here we will have a look at our concentration of our reactants versus the concentration of the products. Remember that when we start a reaction, we start with a lot of reactants. And so as the reactants react together, we form more products. And so the concentration of the products increases as time goes on. Depending on your reaction will depend on the actual shape of the graph as to how high the concentration of the products get or how low the concentration of the reactants gets. So how will the change in a concentration affect the graph of concentration versus time for a reaction that is in equilibrium? First, we'll see a sharp increase in the added substance, or if a substance is removed, we'll see a sharp decrease, and then a gradual change to the other substances. If we have a look at the graph on your screens at the moment, we can see over here we had equilibrium, right? The concentrations were constant, and so that tells us that there's equilibrium. And then here at time 20 seconds, there is a change that occurs here. We have a sharp decrease in our products. Right, remember this started from 0, so this is our product, and there's a sharp decrease which tells us some of the product was removed. So if we remove some of the product, the reaction that produces more of the product is going to be favored, and so that will be the forward reaction, and therefore we see an increase in the product and we would see a decrease in the reactants. The next change is the change in temperature. So when we change the temperature, our reactants and products are affected. One increased and one will be decreased. So we have a look at the graph there. We can see that between time 5 seconds and 10 seconds, our concentrations are constant, which tells us that there was equilibrium. And then at 10 seconds, a change occurs. And we can see that our products increased where both our reactants have decreased, which tells us that one reaction has been favored, and therefore there has been a change in the temperature. Finally, we can have a look at the change pressure has on the system, and when there is a change in pressure, we will see a sharp increase in the concentration of all products and reactants. Remember, the way to increase pressure is to decrease the volume. And so when we're decreasing the volume, the concentration of everything is going to increase. So we change the volume, and so we're going to have more number of moles in a smaller volume, therefore an increase in concentration. However, we know that the equilibrium will shift to counter that change, and so to reduce the pressure, and therefore we'll see a gradual change to restore equilibrium. In this example, our reverse reaction lowers the number of moles, and so our reverse reaction is favored, and so we see a decrease in the products and an increase in the reactants after the initial sharp increase. Let's have a look at this graph of concentration versus time, where there are a number of changes that have occurred to the equilibrium. So if we have a look at the graph, we can see here at the beginning the concentrations are all constant, telling us that the system is at equilibrium. At T1, there is a sharp increase in the amount of nitrogen, which tells me that the concentration of the nitrogen has been increased. Because of this change, the equilibrium will shift to use up this extra nitrogen, and so the forward reaction will be favored, and so we'll see a decrease over here in nitrogen as well as our other reactant, hydrogen. We can also see a decrease there. And because it's a forward reaction being favored, we are producing more of our product, ammonia, and so we see an increase over here of ammonia. The equilibrium is then re-established. We can see that the concentrations get back to a level where they are all constant, and so we have re-established our equilibrium. At time T2, another change occurs. We see a sharp increase in all three substances, so our reactants and our products have all had a sharp increase, which tells me that the volume must have decreased to increase the concentration of everything. When we decrease the volume, we are thereby increasing the pressure on the system, and so the equilibrium will shift to reduce the pressure by producing the fewer number of moles, which is the forward reaction. If we just have a quick look at our reaction there, on the right hand side, the products, we get 2 moles of gas, whereas on the left hand side we have 3 plus another 1. So we have 4 moles on the left, 2 moles on the right. So if we favor the forward reaction, we're producing lower number of moles and therefore decreasing the pressure on the system. So therefore, by favoring the forward reaction, we're going to see a decrease in both our reactants, our nitrogen and our hydrogen down the bottom here, but we will see an increase in our ammonia, our product. And we can see then once again equilibrium is re-established, our concentrations are all constant, they are not changing, and so at T3 we have one final change to look at. We can see that the reactants concentration, both of them have increased, where the products concentration has decreased. This tells me that there was a change in temperature. The fact that the products have decreased and the reactants have increased tells me that the reverse reaction was favored. If we have a look at it, the forward reaction is in fact exothermic, delta H is less than 0, and so I know that my reverse reaction is therefore endothermic, which means I must have increased the temperature in order to favor the endothermic reaction. Let's have a look at the effect of concentration on the equilibrium practically. In front of me I have 3 test tubes with a solution of cobalt chloride hexahydrate. We can see from the balanced equation that our cobalt hydrate ions are pink in color, where our cobalt chloride ions are blue in color. At the moment we have a mixture of these, and so we are getting this lilac purpley color that we have in front of us. However, if we were to change the concentration of one of our reactants, say the chloride ions, we should see a shift to the right of our equation, thereby producing more of the blue cobalt chloride ions. How can we increase the concentration of the chloride ions? We can add some of our hydrochloric acid that contains chloride ions. So I'm going to do that now. I'm going to keep test tube 1 as our base so we can see what the original color was, and in test tube 2 I'm going to add some hydrochloric acid, and we can immediately see that we have a color change occurring there, and it has more of a blue color, indicating that the equilibrium has shifted to the right and to the products. If we, however, wanted to add more of the products, and we should then see a shift to our reactants, to the left-hand side of our equilibrium. And so we can do that by adding more water. So over here I have some water, and in test tube 3, I'm going to add a bit of water. And when we add the water, we can definitely see that we get more of a pink color, indicating that the equilibrium has shifted to the left of the equation. So there we can clearly see the effects of a change in concentration on the equilibrium of a system. Let's have a look at a practical example of how equilibrium is shifted by a change in temperature. In front of me I have 3 test tubes with a solution of cobalt hexahydrate. I'm going to keep one, our test tube 4, as our control, and so we can compare the color there. We can see from the balanced equation that the forward reaction is endothermic. Therefore, if we heat the test tube, the forward reaction should be favored, as that cools the system. However, if we cool the test tube, the reverse reaction, the exothermic reaction, should be favored. Let's have a look. We will keep test tube 4 as our control so we can compare the colors. Test tube 5, I am going to put over here in our hot bath. It's a test tube of water on a hot plate, so that's been heated. And test tube 6, I'm going to place in our ice bath to cool it. And we'll just give that a minute for the effects to take place. If we have a look, we can already see more of a blue color forming in our hot bath, which tells me that the equilibrium is shifting to the products, and so the endothermic reaction is being favored. If I have a look over here in my ice bath, I can also see there's definitely more of a pink color forming, and so that means that our reverse reaction is being favored, and which is the exothermic reaction. So let's just put them all next to each other so we can get a clear comparison of the colors. So here we can clearly see that there has been a change in the equilibrium due to the difference in colors we see in the test tubes. Therefore, the temperature does shift the equilibrium. This brings us to the end of Chemical Equilibrium Part 2. We hope to see you for our next chapter.